Welcome to this last plenary session of the conference. We have 3 talks in this session, and today's session will be held in Lise Meitner Hall. Lise Meitner was an Austrian physicist who played a key role in the discovery of the nuclear fission. In 1905, she became the second woman from the University of Vienna to earn a doctorate in physics and was the first woman to become a full professor of physics in Germany. She worked under very adverse conditions and working on the radioactivity at Kaiser Wilhelm Institute of Chemistry in Berlin, she discovered the radioactive isotope protactinium. Her main work was in 30s, where she actually, when they bombarded thorium with neutrons, they found the new products, and which later they understood as breaking of nucleus. She termed this as nuclear fission, and she also calculated the total energy released in that. And it's literally, this discovery changed the world. The world has never been the same again. Unfortunately, due to given her circumstances at that time, given the political situation, she had to move away from her workplace, and she was already out of Germany at that time. And towards the end of this work, and her seminal contribution was overlooked, and she did not receive the Nobel Prize for this major discovery. Of course, later in her life, she has got many recognitions, and there is a Lise Meitner Institute in Germany now. And I would like to mention that she's the only woman besides Marie Curie to have an element named after her. Now, with this, I invite Dr. Gillian Butcher to chair the session in this hall. Over to you, Gillian.
Thank you very much, Mandana. And good morning, afternoon and evening, and welcome to this final session. We've already had a great variety, a fantastic variety of talks through this last week, and it's going to be the same again. And I'm very pleased to introduce our first speaker, who is Marija Vranic from Serbia. She obtained her MSc degree from the University of Belgrade in Serbia, and her PhD at the Instituto Superior Técnico in Lisbon, Portugal. After her PhD, she was working in extreme light infrastructure in Prague in the Czech Republic before returning to Portugal. Her research is focused on plasmas in extreme conditions, where quantum effects can affect the collective plasma dynamics. She combines analytical theory and massively parallel computer simulations to perform the studies relevant for state-of-the-art and near-future laser experiments using intense lasers. Marija is a member of Young Scientists at the Lisbon Academy of Sciences, winner of the International John Dawson PhD Thesis Prize, the IBM Scientific Prize, Ada Lovelace Prize Award, and the IUPAC Early Career Prize for Plasma Physics. So Marija is going to talk to us today about exotic plasmas in the lab. So Marija, over to you, and we look forward to your talk. Thank you.
So, thank you very much for the introduction. I'm going to share the screen now. So let me just. So when I was asked to give this talk, the organizers asked me to talk about the meaning that this early career EUPAP prize had on my career. So I thought this is something that I cannot talk about for half an hour. And I divided this time in 2. I'm going to tell you a little bit about the research that won the prize. And I want to also tell you about the activities that I've been doing with students locally, and some reflection on prizes and generally what's any honorable recognitions that we have in the communities, and how we can help maybe get more women recognized. So so we're going to start with the physics. Okay, so my research field is exotic plasmas. So when I say exotic plasmas, it means plasmas that are immersed in very strong fields. And this can happen in the universe naturally, if they're like we're in the vicinity of neutron stars or black holes, where you have very strong fields and the particles surrounding that. But also in the lab, we can create this by interacting very intense lasers with matter. And there are quite a few people here to acknowledge in the acknowledgement slides that this is, and they're from several institutions. And this is because we've been collaborating, and including during my postdoc at Eli Beamlines with the infrastructure. This is Eli Beamlines is extreme light infrastructure, where currently they're building the strongest, the most powerful laser in the world. And this is happening in Czech Republic. So I've been doing design studies for their experiments. So I'm a brief mention what is a plasma. So people like to mention that plasma is 99% of the visible universe, but what is important for us in terms of plasma, so you learn in school that plasma is a ionized gas where you have free charges that could be positive or negative. Usually on Earth, we're dealing with ions that are positive and electrons that are negative, but globally this is neutral. But what is important for us is that we have all molecular bonds are broken in the plasma, which means that this material is particularly good to sustain very strong fields. Because if you, for example, want to build an accelerator, you are limited. You have to make a very big tunnel, because you don't have any materials that can sustain a magnetic field of a stronger of a point stronger than some critical intensity. And this is because then otherwise all the materials start melting or burning. And the plasma is in that sense already a destroyed material, so there is nothing more to destroy. And this means we can have very, very strong fields in the plasma, and this gives a potential for making very compact accelerators, for example. So I mentioned that you can have this very extreme state of matter then in the lab by, for example, colliding an electron beam from an accelerator and a strong laser. Or we can also accelerate an electron beam in plasmas, but we'll see this in one of the next slides. And here we have a visualization. This is a pulsar. And here, a lot of you may know. Oh, sorry, I moved it. This is a picture of a black hole. This is how it was in the press, but it's actually a picture of a plasma around the black hole. So this is plasma in extreme conditions. It is emitting radiation, which we can capture on our detectors. So this is it's plasma that's responsible for this big news. And the lasers themselves are everywhere, literally everywhere nowadays. And what we use them for is navigation and communication. We have eye surgery that's called LASIK. So they help us see better, but they also they bring things that are worth seeing. So a lot of artists also enjoy using lasers in their work and light installations. And really, it has penetrated all spheres of our society. So what is different with the lasers that we're using, they're very strong and intense. You can think of them as a strong and intense balls of light. So they're not like these lasers. If you have continuous lasers, you can send the signal very long and the laser doesn't spread, right? And we have, if you have a white light, the signal would spread over the distance of propagation. But if you have a prism, if you point white light in the prism, you will see a rainbow, because the prism separates different wavelengths. So laser usually has just one central wavelength of operation, so it's one color light. And I like to, when I speak with general public, I like to show this comparison. So you can imagine that lasers are just photons propagating in a very organized manner in one direction, like a military orchestra, while white light is something like a mini marathon where you have all kind of people running at their own speed and have very different clothes and very different organization of this motion. So there is no real the laser is, let's say, much more organized propagation of light. And the intense lasers that we are using are made possible by this discovery that was actually given a Nobel Prize. And it was a PhD thesis of this lady, Donna Strickland. She was looking to take a normal laser and make it shorter. So make from a long beam, make a short beam, but very intense, because she needed this to apply for a science project. And they found a scheme how to use a less intense laser pulse that will then be stretched and amplified in some crystal, and then shrink back. So what we have as a result is a few femtoseconds short ball of light that is extremely intense, that can then interact with matter in a very different way than anything that was available before. And since this is extremely nonlinear interaction, when we're studying plasmas that interact with those lasers, we have to use supercomputers. And this is a supercomputer Mare Nostrum that's in Barcelona. It's actually located in a church, because church has really good shadow and it's cold inside, and then the cooling system doesn't have to spend so much energy. So it's actually energy efficient to do that. So what we can do with these lasers, for example, is we can shrink particle accelerators. So if you have your traditional accelerator like LHC in CERN has tens of kilometers across, and you could potentially get the same energy of the electrons in a few centimeters. And this is done by sending a laser through a plasma, and it makes a wake, similarly as a boat makes a wake of the waves in the lake. So the laser generates a plasma wave, and then the electrons can surf on this wave and get accelerated. So the concept is very simple. The laser is so strong. So this is the laser light ball that I mentioned. It pushes electrons from the plasma away and makes a bubble behind it. And then you have this bubble doesn't have any more positive charge in it, but positive charge doesn't have, so the ions, they're heavier than the electrons, and they don't move at the same time scale because they're heavier. So there are still ions inside. So there is positive charge that attracts electrons towards the center. So what it means is that you have also the forces on the sides and forces towards the front. If you have electrons here, they will be always pushed towards the center of the bubble. But now this bubble is propagating at the speed of light together with the electrons and together with the laser, which means that the electrons always, if you fix your view to this window and follow the laser, you will always see the electrons on one point feeling this accelerating field. So they've already reached in the experiments 8 GeV electrons this way. Of course, this needs to be scaled up, but there is big promise, and every year there is some progress in electron energies and beam quality. So we're excited for the future. And also CERN is interested, and they have a plasma acceleration project. So I'm going to just show you how this looks like. We have a laser propagating in a plasma. And now we just imagine you have a camera, and since the laser is going fast, you're just following it as it's going. So if something is propagating at the speed of light, it would look still on this movie. Oops, sorry, should play this. So here we see the electric field of the laser, of the plasma that's created by the laser. So when you want the accelerated electrons, they have to be in the region where the electric field is negative. And this is roughly this region. So if any electrons are here, they will be accelerated. So well, like this, we can get to a few GeVs. There are labs that routinely get there. So my work, so this was actually for my PhD thesis, was to look at now those accelerated electrons while they interact with a very high intensity laser head-on afterward. So here the color shows the electron energy. And what you should see is when this laser interacts with the electrons, it colors them blue, which means they lose the energy. So what's happening is that those electrons are making very rapid oscillations in the laser fields, and they radiate, they emit gamma ray photons. So this means that we can have very strong emission, and we can recreate some of the conditions that are otherwise present only in the astrophysical scenarios. And so we can generate powerful gamma rays in the lab. Okay, sorry. So one of the places that I already mentioned where this kind of experiments will be done is extreme light infrastructure in Prague. This is the building. And the lasers they have are going to be, there are several intense lasers that are going to the same experimental chamber. So one of them can accelerate particles and the other one can be used for the scattering experiment. Another thing that we can do with two lasers, for example, is to put a target, solid hydrogen, for example, and interact with two lasers, one from each side, and make a standing wave that will then not just create accelerated electrons and emit very strong photons, which are in the gamma ray range. They will also be able to create electron-positron pairs. So those are the quantum effects that we mentioned in the beginning. So electron-positron pairs then can continue getting accelerated. They emit more photons, and this is just we call it this QED cascade, where we start from sometimes a very small number of particles in the beginning, but we can create plasma that's very strong. So we're going to see this now. So you can see that the yellow, these are photons, red are positrons that are created in this interaction. And you can also do the electron-positron pair creation in the scattering configuration. So you have an electron beam and a laser scattering, but then the electron beam has to be not few GeV, it has to be 50 GeV, like for example, or at least 10 GeV. So this is a design study for the experiment at Stanford Linear Collider that is expected to create some pairs. So as you can see, only in the most intense region, this scattering will be creating a few positrons. And we are actually collaborating in this experiment. I'm doing the theory and simulation part for this experiment. The extreme light infrastructure in Prague will have two different lasers, 30 femtoseconds and 150 femtoseconds duration. And if we do the same scattering with those two different lasers, we will have different behaviors of the created particles. So if we create electron-positron pairs, but they're still in the region of a high intensity because the 150 femtosecond laser is longer, they have an opportunity to interact further with the laser field and get expelled in different directions. Well, for a shorter laser, the electron and positron pairs are going to propagate in the initial direction of propagation of the electron beam. We can also create optical traps with lasers, like for example, with 4 laser here in planar configuration. This allows us to create different shapes of electron-positron plasmas. And here you can see there is this is the electric field. We're seeing electric field lines in the plane. When the plasma and the plasma density is a surface plot. So when the plasma density reaches the critical density, this is the density where the plasma becomes non-transparent for the laser field. What happens is that all the rest of the light is absorbed and re-radiated in gamma ray radiation. So you can have a very strong interaction of light with this matter that itself created, and these are very clear signatures for the experiment. And this has a very strong potential, for example, for medical and biological imaging. This is one of the applications. We're more interested in the fundamental science, but people are usually more interested in actual applications for the real world, let's say. And one of the big things is the X-ray phase contrast imaging. So this is a technique that is quite simple for imaging the biological samples, or for a patient, it would be doing a simple X-ray. It's just one shot and it's done. But actually, you have an opportunity to reconstruct fully the 3D distribution of the density, and it's very sensitive to small density variation. And this is possible because we have a very small source size, which is characteristics of these strong high photon beams that are emitted from micrometer size source. So, okay, so this is the part that I wanted to tell you about the work that I'm doing. I'm very excited about studying the extreme conditions in the lab, and this is happening in the next few years in many places where there are going to be experiments. And I'm collaborating with them to predict what's going to happen and afterwards and analyze the experiments. And we have an opportunity to create very high brilliance gamma ray and X-ray sources, and they have plenty industrial and also scientific applications. So thank you. This is for this part. Thank you for listening the physics part, even though it was not fully the idea of the conference. But I think it's also important that we show what we do outside of this Women in Physics initiatives. So so this is the work that got me the Early Career Award. And you see the first, I would like to comment on the importance of early career recognitions in general, is that we have, I was absolutely not aware of that before someone nominated me for the first prize that I got. So I got several of them. So I was thinking this is not important, and it's important to do good work, and I'm here because I like the physics and the science, and I enjoy working on those topics, and I have nice colleagues and collaborators and so on. So what I didn't understand is that actually once you get one of these recognitions, you get a lot of doors become open. So first, just the fact that this committee is seeing your even if you don't get the prize, being nominated increases visibility, because the committee is full of important people that will at that moment hear about you. Then next thing is that whenever there are some other opportunities happening, like invited talks are being distributed for important conferences in the field, or people hear about some opportunities or possibilities, they remember your name more likely, and they may contact you, or they're going to say to someone in your group that this is that there is something that maybe you should apply for. So, and the more recognitions are there, the more that somehow this visibility is increasing. So I've found that in the end, those prizes are very important for advancing of my career and for the way that people are seeing me in the field. So now I'm encouraging young students and postdocs to apply for any potential recognition. Even a poster prize at a big conference is something that's important to distinguish themselves for the next steps in the career. So another thing I would like to mention is my activities locally for promoting women in physics. So last year, we created a Women in Physics student club. I'm their mentor, and this is a very nice group. They are I'm sorry, I'm going to share their presentation because I have here 1 second. Okay, so they've done a mini summary at our European Physics Society conference. So we have a Women in Physics lunch on the Plasma Physics Conference of European Physics Society. And so what they've done is they won a grant. So I helped them write the grant application. They won a grant from American Physical Society to start Women in Physics Student Club. And here they are, they're several. So these are two Marianas, Camila and Joanna. There's also Patricia, she's not in this picture, and several others. So this initiative doesn't give a very big grant. It's like $1,000 they got, but it was enough to pay several coffee breaks on several occasions. And they've done really a lot with that. We're organized several role model seminars where we invited people from all over the world, basically, some really famous female scientists to give a physics talk. And then we were afterwards having another half-an-hour session with questions and answers about their career and what are the advice they have for young students. And it was really, really very successful. And they have also did a movie screening about a movie that's called Picture a Scientist, organized several panel discussions, and really created quite a lot of talking at the university level about some of the inequalities and how to address them. And also one of the plans is to do outreach. This was not possible yet this year because there are just few people doing things. But they have also worked with the university to try to put the misconduct procedure in place, which is something very important for like people that are just starting. And I think overall it was very important. So you see that the small grant from your American Physical Society made a very big difference, just because it gave the momentum for the start of the activities. And now these activities will continue, and hopefully the group will grow. And we've discussed with the rest of the university. We're going to connect other departments and try to see maybe to collect information to do some really actions for the future. For example, when there are some awards or invited talks for important conferences and nominations of some kind, maybe we should organize a little bit such that we nominate more, let's say, more frequently our female students and female young staff for things, because they're usually overlooked in physics. In my field, we are 15%. If no one does anything about this, the nominations for invited talks are about like 2 in 80 when I was in the committee and so on. So we have to increase the number of nominated women for them to be able to get the awards and the talks and be able to advance in their career. So this is the first step, and this is the step that we can actually make. So this is up to us. It doesn't have to be from top down, because anyone can nominate. It's just that people don't remember to nominate women. So this is one of the things I would like to change. Okay, thank you very much.
Thank you very much, Maria. That was a fantastic talk. It was a really great sort of taking us through, leading us really nicely through your work and background and where it's leading to. So some lovely work there indeed. And you made some sort of very good points there about sort of, awards and actually nominating, and that is something that we can all do. So that's great. Thanks for your talk.
Thank you very much.
So see, there's a couple of questions. So the first question from Lorena is, how many particles do you have to use for the simulations to simulate the optical traps?
Yeah, this depends how dense is the plasma in the beginning, but our typical simulations can go, it can be 10 to the 10 sometimes, even.
Quite a lot. The next question is from Dr. Mohammed Adnan, who thanks you for this very informative talk. So can you comment on the self-focusing issues with the intense laser beams? And then secondly, wants to know the positron concentrations per unit volume in the lab experiments with respect to the laser energy. Then asks, is there any dependence on the number of positron creations with respect to the laser energy or other configurational features? I don't know whether you can see that.
Yeah, I can.
Remembering
so the self-focusing is something that we actually can use to our favor. So this is a process where if you send a laser through a plasma, it will be depending on, so what it does is the laser in vacuum will focus and defocus. It's like it's a Gaussian beam standard propagation, but in a plasma, after defocusing, then it again can refocus because it kind of creates its own optical waveguide within a plasma. So this is because of the high intensity. So we know exactly as a function of the intensity how frequently this will happen and if the laser will be guided or not. So we usually use, when we are doing, for example, laser acceleration of electrons, we make sure that the laser is in the range of parameters where it will self-guide through the plasma. So we use this self-focusing to our favor. For the scattering experiments and for optical traps, these are shorter timescales, so it's not really, I mean, usually we don't have self-focusing at that stage. We have to focus the laser where we want. And for the, so the other question was about the number of positrons. Okay, so this very much depends on the specific parameters, but to give you an idea, there was an experiment in the 90s, in the 80s in SLAC, which used the 50 GeV beam interacted with a laser about 10 to the 18 watts per centimeter squared of intensity. And this experiment produced 100 photons overall in the whole experimental campaign. So what we believe is that with 1 to 10 petawatt lasers that are going to be able to do these experiments in the future, we will be able to create maybe 10 to the 4, 10 to the 5 positrons per shot. But it's really, so since the rate depends exponentially on the intensity, I mean, giving you a number is just, it's never precise. Okay, so it depends really on the specific parameters, but we expect way more positrons per shot than anyone has ever done in this light electron scattering experiments beforehand.
Thank you very much, Maria. I think we should move on. Thank you so much for answering those questions and for keeping so well to time. That's timed almost to perfection. That was very
Thank you very much.
And if there are any further questions, if people want to put them into the Q&A, then I'm sure be answered sort of in the chat as we go along. So thank you very much, Maria. And we now move on to our next speaker, our next early career speaker. So I'm very pleased to welcome Maria Eugenia Cabrera Catalan, who was born in Guatemala. She received her degree in physics at the University of San Carlos in Guatemala, where she is currently a professor, and her PhD at the Autonomous University of Madrid. She was a postdoc researcher at the Grappa Institute of the University of Amsterdam and later at the Physics Institute at the University of Sao Paulo. Her research is focused on understanding the nature of dark matter and the physics beyond the standard model of particle physics. In 2021, she was a winner of the 2021 OWSD Elsevier Foundation Awards in Physical Sciences. And Maria is going to be talking about her scientific journey towards an inclusive society. So Maria, thank you very much. We're looking forward to your talk. And I hand over to you now. Thank you.
Oh, thank you very much. I will share a screen. Sorry. Sorry, I don't get the. Okay. So is it okay? So can you see my screen?
Yes, we're seeing it and we're seeing it. That's all good. Thank you.
Okay, thank you. So first of all, thank you very much for the invitation. I'm very happy to be part of this conference. So I was asked to talk about my experience and what does it mean for me, what meant for me to get this prize. So at the beginning, I was not sure exactly what to tell you. So at the end, I decided, so I will tell you about what is the experience that I have lived in the last years. And to tell you that, I think it's very important for me to share with you some context about the country, about the situation we are living here, and what does it mean meant for me to, after spending around 10 years abroad for the PhD and postdoc, to come back and to try to build something here. So I will start sharing very few things, but I think that are important from Guatemala. So I'm from Guatemala. This probably most of you haven't heard much about it, so I'm showing you here. It's one of the countries in the Central American region who shares a border with Mexico, and I like very much this this map here. So all these colors represent different languages that speak here. Our official language is Spanish, but there are a lot of native groups that are still living and their cultural heritage from Mayan civilization. So although our official language is Spanish, some of the people that live in Guatemala do not speak Spanish, and this the information that the government shares are not in all these languages, which just tell you a little bit how difficult it would be from some region of the population to get access to education. So I also wanted to show you this beautiful picture. They are from the Guatemala Institute of Tourists. So I just wanted to share a little bit about my country. So it has very beautiful nature. We have a lot of volcanoes. You can see an explosion here. The one of them is very active. Now we have interesting science around, and we also have these Mayan cities in the north, but also very nice Spanish architecture that come from the conquest. So I wanted to tell you some numbers. I know you cannot describe or understand a country with some statistics, but it gives you kind of an idea of what are the kind of things we're actually facing. So I just choose these two plots just to not spend too much time here, from the UNDP report for Guatemala. And this one in the left is the index for poverty. So this is the lack of services in living places. This employment, the green one, is basic services like water, health, this education, and this is technology. And we have a Gini index around 48. And this also thought I also thought it was important to share. And I think since this is an international conference on women in physics, it's also important to mention that the gender equality index, it's very bad. I'm sorry, here. And I think it's the worst in all Latin America. So I know this was very fast overview. Just want to give you a very fast idea of what is the situation we are actually facing. So Guatemala also have the very low investment in science. We have 0.03% of GDP investment in science. And we are actually facing a very difficult situation right now because we have the only public university, which is San Carlos University, and it's involved in a lot of corruption scandals. And this is because as this only public university, they choose some people who represents the university in a lot of governmental institutions. So that means that the university has a lot of powers or at both voice and vote in governmental decisions. And that's been a problem in the last years. So last year was a dean election. I can tell you this is kind of an example. And there was a clear fraud. I mean, the only it was allowed to participate only the people who was in favor of a specific candidate. So it's not that it was not clear. It was clear that it was a fraud. It was not up to that. So there were a lot of protests from students. They shut down several university campus, and they kept the central campus closed for 1 year, a little bit 1 year. So after the pandemic that we were doing every virtual, we didn't came back to the campus. We are still virtual activities because although the students open the campus, the authorities decide that the campus cannot be used right now. So I don't know how long it will stay like this. So the situation I have told you doesn't look very, very good for science. But in the middle of all this, in 2015, the School of Physical Science and Mathematics was created. But this was a very, very good thing for us. Before that, there was just physics and mathematics were part of the Faculty of Engineering. And in 2015, they decided, the main idea was to create a faculty of science, but the idea didn't really went through. And at the end, it was the school, but it was very great thing because they opened permanent position for people and for this. And I was a postdoc in Sao Paulo at that time. And I just came back and I got this position. Although I spent around 10 years abroad, I always thought I want to come back. I always thought I want to be part of creating something here. And right now we have 21 lecturers and researchers, not every people do research, only 4 of us are women. And we have these research areas: higher energy physics, cosmology, astrophysics, complex system, geophysics, medical physics, and applied mathematics. I do particle physics, higher energy physics. And as you can imagine, we are very few in each of these fields. And most of the work we are doing is in collaboration with groups that are in other countries. and only 6 of us have a research, only 6 of us have a PhD. So the situation is quite difficult. But the creation of this physical science and mathematics school was a big thing in Guatemala. Actually, we got in the news, the newspapers came to us, and I think there is a newspaper telling about each of us. I think most of us in the news. And I remember when I was a student, we were three people started the degree in physics, and now this has changed quite a lot. And I think the creation of the school make a very big difference towards the formation of people and to increase research activity in physics in Guatemala. So when I came back to Guatemala, I have this idea that I have to work in the direction of creating a research group like the ones I have been part of in Europe and in Brazil. And it was quite difficult. I think I faced very different challenges that I didn't expect. Someone once told me that, oh, but you're from there. I mean, you grew up there. So why is it so difficult for you to now to really work there? Why do you talk about the challenge, and that's like something it's very, very difficult? I think I spent all the time that I spent abroad, I didn't really thought about how difficult could be to create in a group. So there were many proposals that didn't went through, and I was very frustrated at the beginning, I have to say. But then I have the opportunity to meet Melissa. She's a physicist, experimental physicist, working in LHCb, and she's in Honduras. And we start talking about why do we have to face this alone? Why don't we do it together? And this was very, very nice environment. At that time, I was the only woman professor in this school of physical science and mathematics. So I really, I have to say, of course, it's a single experience, but I have to say that talking with her about how we feel, what we wanted to do, the challenge we were facing was very, very, very nice. I felt that we are a part of something, that we are sharing something. And so we pushed this idea of working as Central American region and not only as Guatemala and Honduras separated. So we organized a first Central American meeting on high energy physics, cosmology, and high energy astrophysics. It was completely virtual. We didn't have money because here, I think asking for some grant or funding, it requires a lot of paperwork. And what we wanted to do is just to know who wants to join our effort. So we organized this meeting, and it was very nice. I mean, there were a lot of participants, most of them from Central America, but living abroad, because the brain in Central America is huge. Also, there are no opportunities here, so people not only prefer to go abroad, but also when they want to come back, sometimes it's not possible. So at the end of this meeting, we agreed to create a Central American network of high energy physics and scientific computing. We oriented it in the direction of scientific computing because we wanted to create a group who include people from other areas that have expertise in scientific computing. Also because this learning, this expertise that we get working in this high energy physics can be also used in other areas. So we wanted to include more people, and that was the idea of the network. So right now, since Honduras and Costa Rica work with some collaboration at CERN, so we want to make this a Central American effort. So we want to that our students can work with any of us And we want to make a group to focus on projects, to try to get funding together, to try to make collaboration together, and to try to define a line of research in the area of high physical and scientific computing as a region. One thing that helps a lot for us to make this network happen was to be part of this Latin American network of higher physics, cosmology, and astrophysics. Because when I came back, and I think I'm not the only one who felt that way, I kind of felt that I cannot follow the groups where I was working before. And this association made me feel I was part of something. And I think that was important, because the effort was from Latin America. There was also more interest from people from Costa Rica and Honduras to join it. So now we are trying to focus on projects, kind of rethinking our strategy as a region to try to keep doing physics, fundamental physics, and using this knowledge and this expertise that we get to try to make bridges with other fields. This is kind of the things we are actually doing, and I'm very happy with this. I think the environment we have created is good. Also, I know we are working very, very slowly, but I think it's in the right direction. So as they mentioned in the presentation, I got the 2021 WSD Elsevier Foundation Award, and as particle physicist doing basic science. At the beginning, I didn't think it was a good idea to be nominated. I mean, the nomination came from the Guatemalan chapter of the WSD. I want to mention this because the chapter was created few months before these nominations, and the environment was great. I mean, it's not common. I mean, I haven't experienced this in other institutions in Guatemala, that a group of women in science supporting each other and getting support. And everybody wanted to be part of this group. And it grew up very, very, very fast. And I think it's very important because, as I mentioned before here, when the institutions are not strong, when there are not very clear paths towards the development of science, it's very important to feel you are part of something. So they nominate me. And after I got it, I got a lot of visibility, as was mentioned before. This prize really gives you a lot of visibility in very different aspects. I mean, I got some invitations from other institutions. I mean, the invitation to this workshop, this conference, it's one example, but also got invitation to share my work in other institutions. And this, I think, was very important. I thought I already have my networks, I already have my collaborations, my group, the people who I work, but this really was very nice, I think, this invitation. Also because I spent most of the time in Europe and in Brazil, and I didn't know much people in Mesoamerica or in Mexico. So it was very good. And also, because students, high school students or primary school students send me an email asking me how I became a scientist. So this really made me smile, I think I would say, because this role model is very, very important. And at the beginning, I didn't realize how important it was for them to see that they can become a scientist. Someone from Guatemala that grew up in Guatemala can become a scientist and get one of these prizes. So what does it mean, apart from the visibility, apart from the new opportunities that I got, apart from that I became close to the people, especially to girls and young people. It also makes me wonder, why did I get this prize? because of the work I did, because of my research in particle physics, but also because I am in a developing country like Guatemala, and I'm trying to facing different challenges. So, for example, I will mention some of the things they were overwhelming me at the beginning. So academia is very competitive, right? The environment, you have to keep very active, get collaboration, publication, citations. And when you are in a group like the one where I belong, like, for example, when I was in Madrid, in Amsterdam, in Brazil, this was I will not say easy, but it's straightforward, I would say. You have to work hard and just keep sharing your knowledge, presenting your work, and it's doable, I think. But here in Guatemala, it becomes a very difficult because I have no resources, there's no group here, and this internet makes things very, very easy, much more than I would say 20 years ago, 30 or more. But still, it's very difficult. It's very difficult to really keep the rhythm that I used to have. And I kind of felt isolation. So project funding was completely disappointing, I will say, because a lot of paperwork, and didn't seem like a very good approach at the beginning to try to get local funding. So I started to focus in international funding, for example. And another thing is that I think we all, the people that do basic science, at some point they ask you, what is the use of basic science, right? And you have to explain the importance of basic science and how it's the base of the development of application technology to make a better society. So this is something that is satisfactory in a country that invests a lot of money, or enough money, I would say, in science and technology. But in a developing country like Guatemala, with very low investment, so I end up asking myself, what is really the use of basic science here? When I came back to Guatemala, in my mind, it was clear that I have to create a group with the same standards that the ones I have been working. But after some time, and especially after getting the prize, I started to make other reflections. So is this really the goal that I want? Is this really the most important part? And I start to wonder and thinking about what is the scientific community I want to be part of. Yes. So being part of these top groups in top institute, it's great. I mean, it's an experience that I really enjoyed being part of this group. But I decided to came back here and to try to build something. I really like this, well, I don't know exactly the words Salam used, but in the speech, when he got the Nobel Prize, he say something that let's strive to bring science to all, so we can make a better society. This was kind of the idea, and this is what I wanted to do. But being here and facing all these challenges, I just understood that I have to work and join efforts to build something. We have to decide what we want to build in a country with these conditions like Guatemala. So what is the role of science and basic science in the development of a society? This is something we have been thinking and trying to incorporate in our strategy. In the projects, for example, that we want to focus as a Central American network, this is a very important point here, because we have to keep in mind the reality where we are living. I have seen that the goal in the university is get more publication, get a better ranking, but I don't think this is exactly how we have to think about our scientific community, about what we want to build here in Guatemala. So we have to think how to make science in a country with the condition that we have. So justice, equity, diversity, and inclusion has to be from there since the beginning. So in this direction, I joined this JEDI committee of the Latin American Association, because I want to learn what other people is doing to include this in the science group, scientific group. And I'm not sure, maybe I run out of time, but I just want to tell you that also the year that I received this award from the out of the BSD and the Elsevier Foundation, I became a mother. So at the beginning, I was happy, because I thought I'm lucky that I became a mother in this time of the history of humanity, when there are takers, when I got keep doing my work and became a mother. But when my daughter born, I started to really understand what does it mean for a scientific career. So the time I used to spend a lot of hours working, and then I have to be a mother. And I wanted to be a mother, and I wanted to be a scientist. And at the beginning, it was very difficult to deal with this, because I feel guilty. I was not doing enough work as a scientist. I was feeling guilty because I was not doing enough as a mother. And then I mentioned this because I think we have to think more frequently, or ask ourselves, what are the scientific community we want to think? Because forming a family is part of what we do as a society, and it's very difficult. It's very difficult to keep the rhythm of publications, of collaboration, of assisting to conferences while you are a mother. So I kind of feel isolated at the beginning, and I also thought, why people is not talking about it? Or maybe people was talking about this, but I didn't give importance to that, because I thought I will be able to keep doing my research and being a mother. So what is the scientific community we want to think? We want to be part of. I want to be part of a scientific community who is aware of the society where it's living, who want to contribute to make a better society, who is open to join scientific projects that involve people in society. And I want to be part of a group who is who include justice, equity, diversity, and inclusion in science from the beginning, not just adding at the end, but from the beginning. Since we have to build something here, I want to include it from the beginning. And I also want to take into account that it's not statistics, it's not a citation or number of publication or ranking of the university, which is important, but is what is the project that we are doing, and how we are focusing to our society to make a better place. And just to end up, I want to share this. NC is a cosmologist. She did the diploma program in ICTP as well as I did. ICTP is an international center for theoretical physics that is focused on developing countries and have this diploma program that helps us to apply to top universities as a PhD. So she is Iranian, and she resigned recently because she was not, she didn't agree with what is happening in Iran right now with human rights. And a few weeks ago, she wrote this in her social networks, and it really made me think a lot. So I wanted to share with you and say may we all be reminded of the importance of compassion and empathy, recognizing that our collective humanity holds paramount significance over any individual project, including science. So this is awesome. So thank you for the attention.
Thank you, Maria. That was a really eloquent and powerful talk. So just explaining some of the challenges and the barriers, but you're sort of very humble in the way that you sort of state them, and it's very clear that you're very passionate and committed, and sort of the achievements. It's really quite remarkable. But we thank you for your talk, and I'm looking to see if there's. I don't think there are any questions, or if there are.
Yeah.
Yes, Angelica has just said inspiring talk, very impressive work. So I think if there are any questions, if you type them in the Q&A, then perhaps we can deal with them or be responded to as we go along. But thank you ever so much for a really sort of powerful talk now, and a great quote to end with. I think that's a very and this someone's just been very inspirational. Actually, our next speaker, which and topics we've had, really cover. It's all fascinating. It's so interesting to hear, and have so many sort of wonderful speakers to be able to talk so eloquently on the subjects, whether it's on the physics, whether it's on the challenges that they face, or whether it's the challenges that society faces. So on that, I think I'm handing back over to Vandana, and I say thank you, and thanks to everyone for their questions and their participation in this session. Thank you.
Thank you, Gillian. So that brings us to the end of a wonderful session, and I thank all the speakers for very inspiring, interesting talks, which have surely given us a lot to think about. And I also thank Gillian for very nicely conducting the session and the question answer session. So we hope to see you in the frame rooms. There are many interesting spots you can see in Twitter, and we hope to see you there. And after the poster session, there at 16:45 IST, there is a resolution session. So let's all meet there. And so with that, we close the session. Thank you very much.
I will tell you after YouTube has started. Just give me a second. So there is a little hit, just give us a second.